about units. So I'm here to tell you now that paying attention to units will make your life easier. After being a physicist for almost 20 years and doing lots and lots of unnecessary suffering, I can tell you with certainty that paying attention to units really, really helps, and it's worth that small little amount of time and effort. I don't enjoy things that are difficult or tedious or pedantic just for fun, but units really are worth all the trouble. Okay, so let's see what all the fuss is about. So, in physics, like in every other science class, we're using the SI system of units. You've got meters, you've got kilograms, you've got seconds, and a couple others that are a little more obscure. Now, these are the base units. Then you can combine them to make more complicated derived units that we'll be talking about later on. So, where did these things come from? So a nice example is the foot. Here's a wood carving from the 1500s in Frankfurt with instructions that says, "Stand at the door of a church on Sunday and get 16 men to stop, tall ones and small ones, as they walk out when service is finished. Have them line up their feet, and then you obtain the right and lawful rod to measure and survey the land with, and 1/16 of 16 feet is the right and lawful foot." Well, okay, that's kind of a mess, but it works. At least everyone's got people around. So after that, we were trying to set up different systems of units, and things got pretty confusing. Now, Europe being monarchies, were often set up units based on royalty, based on the king. That's inconvenient whenever you changed kings. And once the French Revolution was done and all the kings were guillotined, we maybe needed to switch to something more egalitarian. So they set up freedom units, now known as the metric system. This, by the way, is why it's called the SI, because that's the French word for international system, and not the IS like we would call it in English. Well, if metric system is the system of freedom units, why don't we use them here in America? Well, funny story about that. So in 1794, the French sent this guy, Joseph Dombey, to America with an official meter and kilogram to convince the colonies, or the new states, to switch over. He was going to meet with Thomas Jefferson. We were going to adopt the metric system. His ship was blown off course in a storm. He was captured by pirates in the Caribbean. He died in captivity. If it literally weren't for pirates, we might be using the metric system now. So what is this metric system? How does it work? So for a long time, things are based on actual physical objects. So for example, this thing was the official meter bar. Now, it's inconvenient to check because you've got to take your meter stick down to the basement of some building in France and compare it and see how long it is with the actual thing. So when it's something we could actually use in lab. So now it's based on the distance that light travels in a vacuum in a small fraction of a second, and that gives us a good definition of meter that everyone can use. That works great. Unfortunately, the kilogram is still based on this thing. Now, once upon a time, the kilogram was based on the mass of 1 liter of water. If you ever tried chemistry labs, though, you know that can be kind of problematic. But the idea is beautiful, and this is the brilliance of the SI system of units. 1 milliliter is 1 cubic centimeter in size, and it weighs 1 gram, and it takes 1 calorie of heat to raise the temperature by 1 degree Celsius. It's beautiful. But we do still have a problem with our kilograms, though. So first off, it's based on this thing. So if I do an experiment in my lab based on lasers and atoms and interferometers, no matter how precise my experiment is, the results fundamentally depend on the weight of this thing sitting in a vault in France. And as if that weren't bad enough, well, when they made the kilogram, and this was about 130 years ago, they made copies, which is good because you don't want to be the guy that loses the kilogram. Unfortunately, some of those copies now don't weigh the same anymore. Some of them have been getting heavier over the past 130 years. So you could actually say that no one's really certain how heavy a kilogram is right now. Fortunately, there's some groups who are going to go back and redefine the kilogram based on fundamental physics instead of golf ball sized pieces of metal, and hopefully they'll get around to that sooner rather than later. All right, so today's depressing fact. The Johns Hopkins Medicine came out with a press release a few years ago that said medical errors are the third leading cause of death in the U.S., and one of the biggest contributors to this has to do with unit conversions. If I'm going to tell you that this patient needs so many micrograms of medicine per kilogram of body weight, you got to get that conversion right or you're going to have some problems. So, unit conversion saves lives. Okay, today's fun fact, however, is a butt is an actual unit of measurement equal to about 130 gallons. So, back in the medieval times, they were really careful about barrels, and they cared a lot about how much barrels weighed. And so you have these definitions here, and what we see is I could actually take one buttload of something, and that'd give me 130 gallons. All right, so we are now going to be using the metric system. We got to get used to it. The way to get good at this is to come up with reference points. So there's 3 countries in the world right now that don't use the metric system: the United States, Burma, and Liberia. So here in the U.S., we're part of a very small elite group of countries. Now the U.S. will never, ever, ever convert to the metric system, no matter how annoying it is to not do that. You can go look at metrification, the different attempts to do this in the past. It's never gone well. There's a great story from NASA a few years ago where the $300 million Mars Climate Orbiter once crashed on the surface of Mars because of units. So when you do calculations for thrusters and feet and pounds, but the guy who programs them in assumes those numbers were in meters and kilograms, you're going to have a problem. And the thing kind of went kablooey on the surface of Mars, but even still, we're going to stick with feet and pounds, thank you very much. So, let's get used to this. Now, like all things in science, this comes from a great XKCD cartoon that you could look up, but let's think now about how we're going to convert to metric. It's really important that you know what these numbers mean. In physics, when you do a calculation, you've got to know if your answer is right or not, if your answer seems reasonable. And the only way to do that is to know how big these numbers are. So spend some time developing a feel for how big or how small these different things are, so you know if your answer makes any sense or not. So for example, if I'm doing a calculation for room temperature, what should that be in Celsius? So should it be 60? Should it be 10? Should it be negative 10? We need to know. So let's take a look at some examples. So we've got at the top of the chart, 60 degrees is Earth's hottest. Dubai heat wave, Texas heat wave at 40. Now most people know that snow is at 0, so that puts a warm room then at about 25. Now below that, negative Celsius gets cold fast. Negative 40, spit goes clink. Now, negative 40 Celsius and negative 40 Fahrenheit turn out to be about the exact same temperature. Definitely time to go inside when it gets to that point. Okay, well, what about speed? Well, I'm used to driving a car around. My car measures things in miles per hour. So metric-wise, that's, I guess, kilometers per hour, or the SI unit for speed, meters per second. How big are these? How fast are these? If I do a calculation for a car, what number should I get that's reasonable? What about a human? What's a human speed? Well, get used to thinking about this. Imagine laying a bunch of meter sticks out on the floor. How long does it take you to step across one of those? About a second or two. So maybe a human walking speed is about a meter per second. Okay, what about running? Well, I know that Olympic athletes can do the 100-meter dash in about 9 or 10 seconds. So that'd put their speed at about 10 meters per second. So maybe that's running speed. Then I guess cars would go double or triple that. So now I can get a feel for how fast a meter per second is without having to convert to miles per hour or just randomly guess. So let's see what we've got. So yeah, 1.5 meters per second walking and jogging and sprinting in humans. And then beyond humans, we've got your house cats and your rabbits and your raptors and the speed you actually go on the highway and velociraptors on hoverboards. When you do a calculation, you got to know how big these numbers are. If you're calculating how fast a car goes and you calculate it goes 500 meters per second, you should know that that number is ridiculously high. So you got to get used to thinking about the metric system. So yes, there are conversions of units. Some of them are great, some of them get a little bit wacky. Get used to the feel for these. You have a million free phone apps that will do this for you. Google is really good at converting units, but get good at doing it with your calculator or by hand, because paying attention to units really helps out. Take a look at the How to Convert Units video if you want to see some help on that. So, let's now think about how units can help you do well in science and in life in general. Units will help you solve problems, units will help you find and fix mistakes, and units make equations really easy to memorize. So for example, if you are taking physics because you're interested in going to medical school, well, the MCAT has a bunch of physics problems and you don't get any formula sheets. You need all the brain cells you've got, so let's keep track of easy ways to memorize equations for free. Now, as a bonus, if you get really, really good at units, once you get a black belt in converting units, you can do some really scary things like guessing really hard equations just by looking at the units alone. So you can pull up the Schwarzschild radius for the black hole just by guessing what the units are, and it works really well. So let me prove how units can do all these things for you with just one little exercise. Okay, so for example, we're going to deal with waves. I've got these quantities, wavelength, frequency, and velocity, but what's the equation that does these? So lambda is wavelength that has units of length. So it could be meters, feet, miles, doesn't matter, but just some unit of length. Velocity is how fast does it go, so that's length per time. And frequency is a measure of how many waves per second. So that has units of per second, or 1 over time. So just from units alone, pause this video for a second and guess which of these three equations is right. Okay, so it turns out the answer here is equation number 2, v equals lambda f. Why? V is units of length per time, lambda is units of length, frequency is 1 over time, and length per time equals length per time. Or, to put it another way, and I know this is really difficult and mind-blowing stuff, meters per second equals meters per second. Now, just by paying attention to units, I don't have to memorize this equation anymore. I can just write it down. Get good at this game. It really helps. So here's how you play. The rules are pretty simple. Whenever I have an algebraic equation, I have to have the same units on both sides of the equal sign. I've got to have meters equals meters or kilograms equals kilograms. I can't have meters equals kilograms. That's kind of mathematical gibberish. Now, the same thing when I add or subtract. I can only add or subtract terms that have the same units in exactly the way that this sign doesn't. I have 4,663 people, feet, years. That doesn't mean anything. That's like saying what's 7 plus purple. It's just kind of nonsense. Now, beyond these two rules, units are just algebraic quantities. They behave all the laws of algebra that you know. They multiply and they divide. And as long as I follow these rules, I can figure out if the units balance or not. And if they don't balance, then I know I've goofed and I can fix my mistake before I even touch a calculator. So some more examples. If I think about length and mass and time, so here's some examples. Pretend that x and y are variables that are measured in length. So let's just pick meters. M is a mass in kilograms, T is time in seconds. Here's 3 equations for you. One of these equations is mathematically wrong. It's impossible. Whoever wrote this down made a horrible algebra mistake. We can tell just by looking at units. So here's how it works. Number 1, x is length, y is length. Now a number here, like 3.281, numbers are dimensionless, so I can ignore numbers when I think about units. So unit-wise, this is length equals length. That checks out fine. Equation number 2, length equals 3y is still length, so I'm good, plus t. Uh-oh. Meters plus seconds. I can't do that. That's gibberish. I know equation 2 has a horrible mistake in it. What about equation 3? I've got 3yt over 4t. Okay, yt is units of length times time. The t has time, and because units are algebraic quantities, I can cancel out the time in the top and bottom of a fraction. So this equation is just length equals length. So this equation 2 is completely wrong. If I'm solving a physics problem and I get an equation like this that has different units in the terms, I know I've made a mistake somewhere and I can fix it. Okay, so a few more examples just so you can see some written down. So let's take x is length, v velocity is length per time, and t is time. Do these equations work out? So this one, x is length, 10x is length, vt, length per time times time, is length. Yes, that works great. What about this one? Length, I ignore the 1/2. Velocity is length per time. T squared is time squared. So I can cancel out one of these times with this denominator, and that gives me length time. So I have meters equals meters seconds. No, that doesn't work. This equation is wrong. Whoever wrote this equation down made a mistake. So I hope I convinced you that paying attention to units can really help. So your turn now. Here I've got 4 variables: x, velocity, time, and acceleration in length per time squared. I've got 4 equations for you. Pause this video for a second, check the units on each one, and tell me which one is gibberish. So that's it for this lesson. Check out the How to Convert Units video or the other videos in our Learn Physics from ACU series. Thanks for listening.